Hello, everyone, and thanks for joining us, and welcome again to our webinar. As Sasha briefly mentioned, today we'll go over some of our latest research that focuses on YOLOv8 object detection models and how we used techniques like pruning and quantization on our DeepSparse engine to obtain up to 10 times faster models for inferencing on CPUs. Before we get into the details, though, I want to point out over here at the top right of the slide our GitHub page, our Twitter account, and our growing community on Slack. Now, these places can be great resources if you're trying to compress models for your dataset, and especially our Slack community, where we have a number of people engaged in discussions with members of our team. So finding support for your use case can be very easy, and we can help you with your sparsification questions so you can quickly progress on your sparsification path. Well, so let's get started. So as I mentioned earlier, today we are looking at our research on optimizing YOLOv8 models, the detection models for better performance using pruning and quantization on our DeepSparse engine. So the question that comes to mind is, why did we choose YOLOv8 to focus our efforts on? Well, as many of you might already know, YOLO models are state-of-the-art for object detection, and they are the go-to models. And the newer versions, including YOLOv8, are built on top of their original model from 2015 and have proven to be accurate and performant since then, with each version getting better than the previous one in some way or the other. And these YOLO models, they were the first ones to be the first single-stage architecture model that got rid of region-based and sliding window techniques that were employed by some other object detection architectures like RCNN and its variations. But the YOLO models were still able to give better inference compared to these other two-stage architectures. Because with YOLO, you only look once to detect objects and their locations in an image. So with all these YOLO models out there, they have already accrued around 100,000 users worldwide, and this user base keeps growing. For YOLOv8 specifically, it just launched at the beginning of this year, and it has already gathered a lot of adoption, at least on GitHub. According to the GitHub stars, it has around 9,000 already, so that's a pretty good sign. And it also introduced anchor-free detection. So it does away with these anchor boxes, which helps speed up the inference a little bit. So these models also, the YOLOv8 ones, they increase the accuracy at a given inference performance threshold because they are optimized a lot for the GPUs. And previous YOLO versions have also gone beyond object detection and looked at image segmentation and pose estimation and other tasks like classification. And YOLOv8 improves upon them. So, given all this, it makes sense for us to ease the usage of these models and make them faster and more optimized. So I guess with all that's going for YOLOv8, what really is the pain point? As we can see here in the chart, these models have mainly been optimized for GPUs and performing really well on GPUs. But as we see here that the yellow bars here represent their runtime on GPUs. Sorry, this is the throughput, so the higher number is better. So on the GPUs, we see that all these different YOLOv8 flavors, they are performing much better than their corresponding Onyx runtime that's running on a CPU, a 4-core CPU to be precise. Specifically, the GPUs are around 3.5x faster for the YOLOv8N, the smallest model. And as the model size grows, as we go up to YOLOv8X, this difference only grows, and we see that the GPUs are about 10 times faster for these bigger models. So, with GPUs being very expensive, tough to work with, and scarce, and their availability becoming even more limited every day, the big question that arises is, in order to make these, models accessible to an even larger community for wider adoption, and so they can be run on many more devices, can we really remove this dependency on GPUs and leverage CPUs to achieve the same GPU class performance? Yes, we can do that. And that's what we are trying to do every day at Neural Magic. So let's get into some more details here. So today, we'll be showing you some results that we have so far and what we did here and how we made it possible for these GPU-optimized models to be run on CPUs and still maintain GPU-like performance. So we'll first go over our baseline numbers, which just show that the baseline models, when run on our DeepSparse engine, they are up to 2 times faster compared to running them on Onyx runtime. So here we're just talking about baseline models, no optimization applied to them. And our DeepSparse engine is our inference runtime that achieves this GPU class performance on CPUs. And it works on x86 CPUs, so your normal Intel's, AMD's, laptops, and other such devices. And so we'll take a deep look into how we really achieved more optimization beyond baseline models by looking at pruning and quantizing these YOLOv8 models. Specifically, we got up to 10 times smaller models and up to 8 times faster models here. And in the end, of course, we'll show you how you can use these same techniques to compress and optimize your models or use our pre-optimized models and open sourced ones for your own use cases and for your own data sets. So here, we'll take a look at how, by running these baseline unsparsified YOLOv8 models on our DeepSparse engine, we already see some performance gains, as we read previously, when compared to running these models with the Onyx runtime. So let's see here. So in the blue here, we have the YOLOv8 models, baseline models running on our DeepSparse engine, compared to the models, the bars on, in white, running on the Onyx runtime, and they're both running on 4 cores CPU. So the DeepSparse engine already gives you a lot of performance benefit. Because we have optimized the DeepSparse engine to really support these YOLOv8 models, and it does so by using tensor columns that enables faster post-processing operations. And it also uses memory caches on the CPUs, so that enables this faster computation. It also utilizes efficient high-performance scheduling and JITs to get faster matrix multiplications. So how much improvement are we really seeing over here? You can see for the YOLOv8N model, the benefit is around 2.3x. And as we go up to the larger YOLOv8X model, the benefit goes up, to around 1.8x. So we see some benefit just by using the DeepSparse engine. So, I mean, hopefully those results gave you an idea of what's possible with using just our DeepSparse engine. And now let's ask the question whether this gain that we saw with the DeepSparse engine can be further improved when we add sparsification on top of that. And yes, we do see a big improvement. We see up to 8 times faster results by using quantization and by pruning-like methods for optimization. So pruning, as many of you might already know, is a way to make a network a bit more lightweight. And we do this by removing some of the weights and connections from the network that is typically over-parameterized. And what we get is a sparse network with fewer connections compared to the original network. And because of these fewer connections, we have fewer computations, so it runs faster and is also smaller in size. So for our case, what we did is we compared various sparsity profiles to get the best performance accuracy trade-off. And then we ran extensive experiments with this selected best sparsity profile to find the best pruning algorithm which would recover the most accuracy for the YOLOv8 case. And we were able to achieve upwards of 95% accuracy recovery while maintaining the most compression performance benefits for the various YOLOv8 models. And then we looked at quantization. So quantization just compresses the floating point weights down to int8 or lower at times, but we look at int8 quantization here. And it can be applied on top of pruning and combined with pruning to further compress the models and to add performance improvements. So we first compared various one-shot and training-aware algorithms to find the best optimizations for both dense and sparse models. And then we were able to get fully quantized int8 model graphs while keeping the impact on accuracy to a minimum. So let's get some details about these steps next. So like I mentioned previously, we compared different sparsity profiles in order to find the best one. And that is important to do in the case of detection models, because typically detection models are harder to prune and can be tricky to get a good trade-off between performance and accuracy. And the big reason for this is that unlike another model like BERT, for example, a detection model has different layers which react very differently to pruning. So for example, the earlier layers will recover less effectively, while the later layers, they give you more of a boost in speed up with pruning. So this gives us this sort of an optimization problem where how do we really pick the best sparsity for each layer to get the best for both performance and accuracy? So what we did is we first chose the best sparsity profile by looking at a number of different one-shot methods for generating sparsity profiles. And here we looked at one-shot methods because this keeps the experimentation part faster, and we can look at a number of methods. Here we kept OBC as the pruner, and we looked at three sparsity profile generation methods: uniform, global magnitude, and speedy. I think uniform and global magnitude are pretty well known, where uniform prunes all layers equally, and the global magnitude one kind of focuses on the weights. And speedy is a newer one where it learns efficient sparsity profiles using dynamic programming search. So it essentially uses timing information for the different layers as measured on hardware and tries to create an optimal sparsity profile based on that. And if you want to learn more about this approach, I'd encourage you to take a look at this paper, which was produced by one of our collaborating research scientists, Dan Alistair, and his team at ISTA. So now let's take a look at the results for some of these sparsity profile generation techniques. So here we are looking at throughput speedup and the accuracy recovery with the OBC pruner. The blue curve here is the uniform sparsity profile generation method. And each of these data points represents the target sparsities that we were looking at, starting from around 50% to 75%. We have a bit more for the global magnitude method. Here, as we can see, the uniform method doesn't recover accuracy very well, whereas the global magnitude method recovers accuracy pretty well, especially for lower sparsities, and then goes down a bit more. But speedy really gives us the best balance between accuracy recovery and the performance benefit that we get. So we found speedy to be a better method overall, and we picked this for our further training-aware experiments with pruning. That we found a good method for generating these sparsity profiles, we wanted to use training-aware methods to find a method that would maximize sparsity for a given accuracy recovery. And we chose the sparsity profiles using a one-shot approach, as I mentioned, because it's faster and we can try a lot of different methods out there. But training-aware methods typically produce better recovery, especially at higher sparsities. So here we'll be looking at the different pruners in the context of training-aware. And the two main pruners that we looked at are global magnitude pruning and OBS, optimal brain surgeon. So looking at global magnitude pruning first, GMP is a zeroth ordered method that looks at the magnitude of weights for the individual nodes and prunes the ones that are lowest. And it prunes as many of these lowest weights as needed to get to your target sparsity. So using the sparsity profile, the speedy sparsity profile that we generated in the previous step, we looked at optimizing hyperparams for the GMP method, and we ran several experiments, and we targeted some of the general hyperparams like initial and final learning rate, the learning rate schedule, linear or cosine, which worked better, and even the total number of epochs. And we also tried searching for the best GMP-specific hyperparams, like the number of pruning epochs within these total number of epochs that gave us the best result, and the pruning frequency, either linear or cubic, what worked better for this GMP pruner. And we also looked at OBS, optimal brain surgeon, and you might know that this is a second-order method where you really look at the approximation of the curvature of the loss, and this method really tries to prune weights that would affect the loss the least. So in this case, again, we used the same sparsity profile that we found in the previous step, but we took the general hyperparams that we obtained using our GMP experiments and used it for the OBS part, but we trained specifically for the OBS-specific hyperparams like Fisher block size, dampening factor, and other ones that really help approximate the Fisher approximation in the OBS method. And what we found was that both GMP and OBS were very similar. GMP was just slightly better. So we chose GMP for its simplicity and because it's also faster than the OBS. And we used the GMP method for pruning the different variants of the YOLOv8 family. On top of pruning, then we also looked at quantization that I mentioned before. And as you might already know, that the YOLOv8 models are stored as 32-bit floating point format, which can take up a lot of memory, and it's especially tough when you're trying to deploy these larger models. But these can be compressed down to an 8-bit integer representation for faster compute and smaller storage. So for quantizing the YOLOv8 models, we explored 3 algorithms, and broadly these fall into 2 different categories, where one is where you quantize after training, and the other one where you quantize during the training process itself. And for this post-training method, we looked at the standard PTQ, post-training quantization, and a newer method, the OBQ method, optimal brain quantization. This was also developed by Dan Alistar and his team at ISTA. This is an extension and is based on the original OBS paper, but this method can be quite time and space efficient and can give better accuracy recovery compared at least to PTQ, and they are both one-shot methods. We also tried a training-aware approach, the quantization-aware training for the pruned models. And let's look at some results here that we got. So PTQ, the darkest blue here, is the one where we got the least recovery, at least for the dense models. So these are the dense YOLOv8. This is the dense YOLOv8 S model. And we compare it with the pruned 50% YOLOv8 S and the pruned 65% YOLOv8 S model. So for the dense models, as we can see here, the OBQ method performed better compared to the other two in recovering accuracy. And for the pruned models, for both pruned models, the quantization-aware method, QAT, performed slightly better than the other two methods. So we used QAT for quantizing our sparse models, and we used OBQ for quantizing our dense models. So now let's go over some results. So first, let's start with taking a look at how our pruned and quantized models on the DeepSparse engine give up to a 6 times better latency, all with around 95% accuracy recovering from their corresponding baselines. So here we're really looking at latency compared with the accuracy here, and smaller numbers are better. And as we see in the blue curve here is our sparse quantized models being run on the DeepSparse engine, and the red curve here represents dense models being run on the Onyx runtime, and they're both running on 24-core CPU. So we see that the YOLOv8N model is faster than its corresponding N model, the dense model, by about 6 times, and the YOLOv8X, the largest model, is about 5 times faster than the corresponding dense baseline. And an interesting point and a very promising result over here is that the YOLOv8L model inferences faster than a baseline YOLOv8 nano model, and still gives you much better accuracy. So you could deploy a larger, faster and better model using our sparse quantized DeepSparse method. So that was a look at latency, and now let's look at throughput, how we're doing here. So here we are looking at the small, medium, and large models, and the throughput for these. The larger numbers are better. So the blue here is the DeepSparse engine, which is running our sparse quantized models. And the middle shade is the DeepSparse running the dense models, and red here is the Onyx runtime running dense models again. So we already see that the DeepSparse engine gives, with the sparse quantized models, gives you a much better gain in performance. How much? Not shown here, but for YOLOv8N, we see about an 8x improvement, and for YOLOv8X, about 6x improvement. And I think that's really given in these numbers for the other models here as well. And we see that the larger YOLOv8L model here with the DeepSparse engine and sparse quantized is about 1.8x faster than the YOLOv8S model that we can see here. So again, a larger, more accurate model is something that you can go for instead. So those were the latency and throughput comparisons. And now let's look at how we compare against GPUs. So here, what we're seeing is that, again, the sparse quantized models are running on DeepSparse are in the blue. The dense models running on the GPU are in the yellow, and dense models running on the Onyx runtime on the CPU are in red. DeepSparse is also running on a CPU. So these are the CPU ones are running on 8 cores, and we see that the GPU numbers are around 5 times faster than the Onyx runtime for this 8-core CPU here. So the GPU is really fast when you run any of the YOLOv8 models. But what we also see here is that the DeepSparse numbers are either equivalent to it or faster in many cases. So specifically for the N model, the GPUs are about 2.5x faster, and for the X model, about 5x faster. And putting sparsification and quantization along with our DeepSparse engine, you can get similar or better performance compared to the GPUs. So now, I think assuming that you've been using our optimized YOLOv5 models, or if you want to consider the YOLOv8 models, should you actually go for it? So yes, we recommend that you do, because all of the YOLOv8 models are accurate for a given speed or faster for a given accuracy than the YOLOv8 models. And here we see the YOLOv8 models are in the blue curve, and the YOLOv8 models are in the white curve here. So for example, the YOLOv8N model, the optimized YOLOv8N model, is more accurate than the larger YOLOv5S model, but the YOLOv8N model inferences faster than the YOLOv5S model. And also the YOLOv8L model is more accurate than the YOLOv5X model, while being significantly faster. So here, what we are really seeing is that with YOLOv8, we've enabled a shift in the accuracy performance Pareto front. So that was a lot of charts, numbers, and text. So now let's see it in action. So here what we have is the YOLOv8M pruned and quantized model running on the top on our DeepSparse engine. And at the bottom, we have the YOLOv8M dense model running on the Onyx runtime. And as you can see, that we achieve about a 5-time improvement in performance with our pruned quantized model running on the DeepSparse engine. And it really is almost real time, and it gives you much better performance than just compared to the Onyx runtime running the dense baseline. Okay, so let's go and see. Hope the results that we have showed you so far are compelling enough for you to want to give our optimized models and engine a try. And now we'd like to show you how easy it is to actually get started and run it yourself. So first, if you want to check how any of our models will perform for your hardware, you can simply pip install DeepSparse and then run our benchmarking command, DeepSparse.benchmark, to check the performance. And this is an example of the output that you might see. And then you can make a decision about which optimized model might work best for your setup. And for running it on your hardware, then there are really a couple of ways to run inference using one of our sparsified models. You can either integrate it into your Python code by importing our DeepSparse library and using it to download a sparsified model from our open source repository, and then running your images through for inferencing. Or you can also deploy a sparsified model onto a local DeepSparse server, and you can run inference on your images over HTTP. So you just point to the model that you want to use and just call the DeepSparse.server command. You can also use our DeepSparse command line interface to run inference and annotate your own images or video. And here we see an example of how to use this command. So just simply say DeepSparse.YOLOv8.annotate, give it your image and the model paths that you'd like to use for annotation, and you see an example of the image annotated down here. So how would you really deploy something that you have? So we've been talking about our open source repository. So what we call our open source repository is Sparse Zoom, and here's a link to that repository. So it has a lot of sparse models pre-trained on datasets ready for you to fine-tune. You can also find dense, quantized, and other flavors of YOLOv8 models, and a lot of different other models if you'd like to use those. So you can scan this code if you'd like. And if you want more answers to some of the how-tos about YOLOv8, you can check out our documentation for YOLOv8 on DeepSparse. This is the page for that. I'll just pause here for a little bit so you can capture these. And so far, we've been showing you results on the COCO dataset that the YOLOv8 family of models was originally trained on. Our pruning and quantization was also done on the Coco dataset. And as you are well aware, for running inference on custom datasets, you first typically transfer learn onto that custom dataset. So we can do the same here for our sparsified models, and we call that process sparse transfer. So this process preserves the same level of sparsity as the starting model. So here, what we did is we took our optimized YOLOv8 models, and for the dense models at least, we used standard transfer learning. And for our sparse transfer models, for sparse transferring the pruned models onto the VOC dataset, we use the sparse transfer process. So here we are seeing numbers of the sparse transfer process onto the VOC dataset for the different models and how they recovered accuracy. The sparse models are in this dark blue shade here, and the dense models are in the lighter one. And we see that the sparse models actually recovered to and outperformed their dense baselines here. So you can sparse transfer onto your custom data as well. So sparse transfer learning is the easiest pathway for creating a sparse model fine-tuned on your dataset. So like we showed, it works by taking a sparse model pre-trained on a large dataset, for example, the Coco dataset that we had previously, and fine-tuning it onto any smaller downstream dataset and your own custom dataset even. So it's pretty simple. You just pip install Sparse ML with the Ultralytics option and use our command line interface to start the sparse transfer process. So here there are three main arguments that you need to really provide: the model, the recipe, and the data. So the model specifies the base model that you want to start the transfer learning process with. And you can find one of the models from our Sparsu that we mentioned previously. And also, you can provide a recipe. A lot of recipes are available on our repository again. And you can take one of these recipes directly, use it as is, or tweak it a little bit if you want to, or even provide your own recipes if you have something. And the data path here where specifies the data set that you really want to fine-tune the model on. So by using this pre-sparsified models for your data set and just fine-tuning it, you can avoid a lot of time, money, and hyperparam tuning that is involved with sparsifying a dense model from scratch. So the recipes, like I mentioned earlier, can be found again on our Sparsu, and you can scan this link. And for all other Sparse ML related documentation on YOLOv8 and even other stuff, you can go to Sparse ML, but specifically for YOLOv8, you can find it here at this link. Just scan it if you'd like. So we've covered a lot of ground today, but before we wrap up and get into some questions, I just want to quickly tease out what's coming next. For YOLOv8, we have more features in the pipeline, and we'll be working on instance segmentation and pose estimation. For segmentation, we already have base models available on Sparsu, and we'll be adding pruned and prune quantized models to Sparsu very soon. And later this year, we'll also be adding YOLOv8 pose estimation models. So apart from YOLOv8, our team is also working on other interesting products and services. So first, taking a look at Sparsify, which is our ML as a service offering, where you can either easily sparsify your own models from scratch using a one-shot approach, or use pre-existing models for your own custom datasets for fine-tuning using sparse transfer, or use training-aware methods for even more control. And all of this is available on the cloud, so it makes it very easy to use. And we are also expanding the footprint of our DeepSparse engine by enabling it on more architectures. So for like Apple Silicon and ARM, and you can deploy these anywhere from your smaller devices to laptops to cloud. So I guess, all right, that's all I wanted to go over today. And if there are any questions, please, let's get to them.
Great. Thanks, Shubhra. And we have quite a few questions coming in. So let's go and run through those. We've answered a few so far, but saved a little bit for the end here. First one is how to use DeepSparse for their model on a custom data set.
So I guess where we specified earlier, you can use the sparse transfer process. Let me just go back to that. Here, yeah, so you can just use install Sparse ML and use this command here and use either this recipe or there are several other recipes that are available on Sparsu and start from there. That should get you going on your custom dataset path.
And then another one, any hardware performance comparisons of Raspberry Pi like edge devices?
I don't think we've done any edge device comparisons yet, but that's a great point. I think, I don't know, Mark, if you have more to add to that.
Yeah, we haven't done YOLOv8 on Raspberry Pi or anything yet, but we do have our DeepSparse Alpha out currently for ARM, and we're moving to beta within the next few weeks on that. That is specifically targeted at server ARM chips, and we are actively working on both Mac and more, well, I should say smaller edge devices, where we get closer to Raspberry Pi. So not yet, but we do have some initial results on server ARM for other models like BERT and LLMs, and those are looking very promising. We're seeing around the same speed up that we see for these x86 style architectures as well. And then we have another one. How are the techniques different and effective compared to Intel's popular Openvino?
So for comparison against Openvino, I don't think we have any direct comparison. That would be interesting to do as well. But as you saw, that the results that we showed you today, they are pretty effective. But for comparisons, we don't have that yet.
Yeah, and I should say that, well, just kind of, oh, sorry, I think my headphones are dying. Apologize on that. But just running through a direct comparison of Openvino versus Sparse ML and Sparsify, the tools that we have out currently. So Openvino exclusively applies post-training quantization for their setup, at least for anything that they're doing in post-training or one-shot. And additionally, they have magnitude pruning. So the algorithms that we're using here, such as Speedy and OBS and OBQ, things like that, those are all specific to Sparse ML and Sparsify and are essentially the research that we're working on productizing and pushing out to everyone. So Openvino is really comparable and pretty close to what PyTorch has built in, as well as what TensorFlow and Keras, like TF-Lite pathways, what those had built in, which is to say that they have, things that were popular 5 or 7 years ago in terms of optimization algorithms. And going through Sparse ML and Sparsify, you kept much more up to date with current state of the art research. And that's kind of the core difference between them, other than more cosmetic pieces like ease of use and things like that, which we push quite a bit around as well. We had another one about, can the optimized models run on ARM CPUs, or are they specific to x86? I think we covered this one overall. So ARM support is coming. We haven't tested YOLOv8 on it yet, but I expect to have that out in a few weeks. And so currently the numbers that we showed were all specific to x86. We have another one that says, if I use any unstructured prune model in DeepSparse Engine on an Intel CPU, I understand I can see a benefit in latency. Can you please confirm that? Instead of a model from Yuzu, if I have my own model, can you please point me to an example on your website if available? So towards the website, I am trying to pull up a link to that real fast. It's on our docs website where we do have examples for using your own models. Definitely fully supported from that standpoint, provided that it is a standard Onyx graph for convolutions and fully connected layers. Then DeepSparse will run that for speed up across those. One notice that you will want, in terms of sparsity levels, you'll want to be above 50%, usually around 80 to 90% is kind of the sweet spot in terms of getting significant speedups. And while pulling up those docs to share out, let's go ahead and move on to the next one. And we have one that says, could you please elaborate more on how your training function works? Does it do pruning and quantization after this training on our custom data set?
Going back to this again. Yeah, so here, what you're doing is you're really fine-tuning the model onto the custom data set. And if you want to add quantization to it, that can be done as well. So I think all you need to provide is your custom data set and the recipe. So if the recipe specifies a quantization bit, then it will also add the quantization in there. And I think we do have examples of recipes that combine both in the same recipe. If you want to take a look, I think YOLOv8, we might still need to push those out, but we definitely have examples from previous YOLOv5 iterations that could be modified for this. But definitely reach out on our Slack channel and we can get you started with that.
And then we have another question. Can I do sparse transfer learning on commodity CPUs? And if so, what are good CPU specifications for training? And I think Shubhra can dive into that one a little bit more from an so in terms of training on CPUs, we don't have that supported currently through DeepSparse. It is something that's on our long-term roadmap to be able to enable. There are some pathways that you can go about doing that. We actually have a paper out specifically for image classification that shows being able to do sparse transfer on CPUs. And specifically what we did is we froze the backbone of the network. So whether it's pruned or pruning quantized, freezing that backbone. And what that means is we can run that in an inference engine like DeepSparse. So we get the significant speed up from DeepSparse on technically that training pipeline. And then we just add an extra fully connected layer on the end to be able to fine tune to whatever the new data set is. That works fairly well. There definitely are some use cases where it doesn't, in the event that the data set you're trying to transfer to significantly differs from the upstream data set that it was originally trained on. From the object detection standpoint, though, we have not tried that, and there may be some more issues with that, specifically because object detection isn't just a fully connected on the output. We have multiple convolutional heads on the output, especially for the YOLO networks. So it's definitely something to look into more. And if you'd like, we can connect through our Slack community and dive in a little bit more. We have another question asking if we can convert sparsified models to core ML. This is something that is, especially with our ARM push, is in progress for us to evaluate. As I said, we're working on Apple support currently. So stay tuned on that. It's definitely something we're actively looking into currently, but cannot convert with our with the state that's pushed out now. And then another quick question: what's your licensing method, and is it on the model or per user for final software?
So all of the models that we have up on Sparsu are open source, so you can go ahead and use them. So I think that's really it.
Yeah, for all the models, those are all free to use. The sparsification software is all free to use and open source. For DeepSparse, it is free to use for community and research. And then we have licensing available for enterprise use cases. And that's charged for DeepSparse is charged per core on deployment. I'm trying to parse this one. I think it says, what is the runtime after using DeepSparse? I mean, is it an Onyx output so we can use it on Edge? Or in other words, how can we use your model on different hardwares like Edge? Yeah, so all the models are in an Onyx format. So anything that will run Onyx models will definitely be able to utilize utilize these. One note is that for the pruning pathways, the only inference engine enabled on CPUs currently on Onyx is DeepSparse. So you won't see speed up from the pruned ones, but you definitely, provided that the inference engine supports quantized graphs, then you'll see speed up for those on other times. All right, and then we had another question just building off of open source and Openvino. So in terms of the open source that we have, Sparse ML, our sparsification framework, is fully open source. The Sparse Zoom, all of our sparse models are fully open source. DeepSparse, the wrapper and pipelines are open source. And the proprietary software that we have around tensor columns, scheduling, JITs, things like that, that is closed source and kept proprietary. And then final question coming in, do I understand correctly that one, I can train a YOLOv8 on a custom dataset and then use DeepSparse? And two, I can customize the YOLOv8 architecture and then use DeepSparse. So the customization being add a second head, for example.
So for the first part, yeah, you can definitely train a YOLOv8 model on your custom dataset and then use it on the DeepSparse. So the second part is, can you customize YOLOv8 architecture and add a second head, for example, you said? I believe that might be possible as well. And then you can use it on the DeepSparse engine.
Yeah, definitely. The one notice that you have to export into the Onyx format, which we provide tooling for. But yeah, otherwise everything fully supported and shoot stuff. All right, great. And then let's see, we had another question coming in the chat on documentation. So Shubra, if you could pull up those links real fast for Sparse ML and DeepSparse. And we'll be sharing all of these out as well after.
Yeah.
The bottom one here is for
Sorry.
Sorry. Yeah. The bottom one here is for Sparse ML. So you can see the YOLOv8 docs for how to sparsify models and Spark transfer. And then Shubra, if you pull up the DeepSparse one. Perfect. And then this one is for the DeepSparse docs, where you can look at the inference engine and get into deployment for all the models that we have on Sparse Zoom. So again, we'll be sharing out all these links afterwards. So keep an eye out in your email as well as on social through LinkedIn and Twitter. And I believe that's all the questions that we have come in. So thank you everyone for listening in. Thank you, Shubra, for presenting all this great research. It was, yeah, it's always fun to be able to push out new state-of-the-art things like this.
Absolutely. Thank you so much, everyone.